This is the Gravitational and Electric Fields Homework Booklet, questions 6 to 8. So we have two masses, m and 2m, exerting a gravitational force F on each other when they are a distance of r apart. Based on that, you are asked to suggest what the gravitational force will be when you have two different masses, 2m and 4m, and they are 4r apart. So this is just a comparison of the two situations. So here we have an expression for the original force based on the equation G m1 m2 divided by r squared. So m1 m2 gives you 2m squared. And then you repeat the same use of the equation with the new data. So we have G times the product of the masses, which is 8m squared, divided by their separation squared. Do be careful, this 4 needs to be within the brackets, and so it is squared, becoming 16. Simplifying the maths here, you can just cancel down, getting an expression of gm squared divided by 2r squared. The final step is to compare this value with the original. We have 2 on the top line here and 2 on the bottom line here, so we can see our second value is a quarter of the original. So answer A. Next, you are asked to look at some data referring to two different planets, P and Q. We have their radii and we have their density. You are also told the gravitational field strength at the surface of P, which I have recorded here. And the challenge is to find the gravitational field strength at the surface of planet Q. So this is to do with comparisons, ratios, identifying the relevant variables that are going to impact on your answer. So starting with the equation for the gravitational acceleration, gm divided by r squared, we want to relate that to the information that we have been provided with. So the mass of the planet will equal the density times the volume, and the volume will be the volume of a sphere, 4/3 pi r cubed. Just cancelling the radii here leads to an expression of the gravitational constant times the density times 4/3 pi r. The g and the 4/3 pi are simply constants, so the gravitational field strength is proportional to the density times the radius. Looking at those values then, those are the things we have in our table, and you will see that the density times the radius is actually the same for each planet. So you have double the radius but half the density, leading to the same value. That means that the gravitational field strength will also be the same as before. Finally, question 8. The gravitational field strengths at the surface of Earth and the Moon are given as 9.8 newtons and 1.7 newtons per kilogram. You are told the mass of the Earth is 81 times the mass of the Moon, and asked for the ratio of the radius of Earth to the radius of the Moon. Although this question is a question set in the context of gravitational fields, it is very much a skills question of being able to handle expressions and use ratios. So you can learn from this in a wider way. So looking at how to approach this question, I have been given two values for gravitational field strength, and I'm ultimately wanting to relate this to radii. So starting with the known expression for gravitational field strength, we have that equals gm divided by r squared. I know I want ratio of the radii, so I'm going to rearrange that to give me r squared equals gm divided by the field strength. And then taking the square root, I now have an expression for the radius. So now I want to build up the ratio, so I have radius of Earth to radius of Moon. And that is going to give me a fraction divided by a fraction. So just using this expression and putting in the subscripts so that I'm referring to the relevant data both for the Earth and the Moon. Now be careful, to divide by a fraction you want to turn the fraction you're dividing by upside down and multiply. You can see I've dropped the gravitational constant because that cancels. So I have ME divided by GE, that's here, and then I'm turning this part upside down and I get GM divided by MM. You'll see I've grouped the masses together because I know the ratio of those two masses is 81. So just finishing off the maths leads me to an answer of 3.7.